Okay, we're still interpreting Bode plots of a forward path transfer function to find out things about the closed loop performance. In a previous video, we talked about phase margin, which itself is a performance measure. It's a measure of relative stability, how close to being unstable or stable your closed loop system is. But phase margin can also tell us about other performance measures, both time domain performance measures and frequency domain performance measures. If we use the dominant pole concept and think about the prototype second order system. Remember, for one thing, we're talking about the Bode plot we have is of the forward path transfer function in a unity feedback configuration. If your closed loop system is a prototype second order system, then this forward path transfer function could be as given here. And we can calculate or have a translation between phase margin and the parameters of the second order system. We can kind of go back and forth. If you give me phase margin, I can tell you what the natural frequency and the corresponding damping ratio would be for a prototype second order system. We're not going to use these formulas directly, and I'm not going to go through the derivation of these. There's more in my typed notes on my website. Consider it an exercise for the reader. But that's the idea. We're using a prototype second order system and sort of the dominant pole concept to do approximations. So let's talk about some frequency domain performance specifications. Here's maybe a sort of typical spectrum over frequency. And here we're talking about now we're talking about this M being the closed loop transfer function. Down at zero frequency, you'd have some gain. We call it the DC gain. And then there would be some maximum gain over all frequencies. So there's the frequency where that maximum occurs. There's what is the maximum expressed as a ratio of this DC gain. And then what we call the bandwidth of the system, which is where the gain goes below 1 over the square root of 2. That's by convention. So we have sort of 2 or 3 more performance measures. Now these are in the frequency domain. And there's also the time domain performance measure. And a lot of them could be translated from the phase margin. I won't go into all these derivations, but the bandwidth can be calculated from the damping ratio. And there's a formula that corresponds that phase margin can give you damping ratio. If you go back here, phase margin depends only on damping ratio, so you can go both ways. You give me the damping ratio, I'll give you the phase margin. And now there's a relationship between damping ratio and bandwidth. So, and by the way, here's what that gain can look like over frequencies. For very small damping ratios, you get bigger and bigger overshoots in the frequency domain. In fact, if the damping ratio is 0, it goes off to infinity here. That's actually, I believe, an unstable system. Once the damping ratio goes above 1 over the square root of 2, it doesn't go over the DC gain at all. See all these larger damping ratios, they stay below the initial DC gain. So you only have overshoot at all if your damping ratio is smaller than 0.707. And we had these time domain specifications, performance specs, again, related to damping ratio and natural frequency for a prototype second order system. So a lot of things go together. Your peak overshoot in the time domain and the frequency domain both depend only on that damping ratio. They both get bigger as you damp it less, as the damping ratio gets smaller. Increasing your omega sub n increases your bandwidth and decreases your response time, and I guess also your settling time. So the higher your bandwidth, the frequency domain, means the faster response. You can think through these, read my write-ups on my website. So instead of all that formulas I just showed you, we use these graphs. Put these on your formula sheet. That's what I gave my students when they took exams and did homework. So instead of having a formula you need to put in the calculator, we're just by eyeball using these graphs. Again, everything is pretty approximate. We're already doing basing it on the dominant pole concept, etc. And actually, we're going to be using this one on the left more often, I believe. Let's look at that a little bit more. On this graph is both the peak overshoot and in the time and frequency domain continue to the right. Let's see, peak overshoot is the blue line here. Once you get above about 75 degrees, it just stays at no overshoot, 0% overshoot. And for the M sub R, the overshoot in the frequency domain, maximum overshoot in the frequency domain, once you get above here, it just stays at 1. It doesn't go above the DC gain. On the other end, let's see, where this M sub R, where the red goes off the chart, I told my students just call it big or something over 4.5. It's just going to go off to infinity as you go down to 0. So I just said, I told my students just call it big. And if the phase margin looks to be near 0, just call it, give it a peak overshoot of 0.99, almost 100% overshoot. Let's see. Phase margin will determine stability. If it's negative, your system's unstable. It's greater than 0, it's stable. Less than 0, it's unstable. And how big it is kind of tells you how close to stability you are. By the way, if your closed loop system is unstable, none of your performance measures mean anything. So let me quickly, how would you use these charts? Somebody says the phase margin of your system, which you got from the Bode plot of the forward path transfer function, what peak overshoot in the time domain? Well, let's see. Phase margin is 50. That's here. Peak overshoot is the blue line. Go up. Okay, it's right there. Something a little bit below 20%. We'll call it 10%. How much peak overshoot you'd expect in the time domain. What if your peak overshoot spec is 30%? And peak overshoot is the blue line. Here's the blue line, and the left side is peak overshoot. 30%, it's the blue line, that's right there. What's the phase margin there? About 40. What if I have the peak overshoot in the frequency domain of 2.0? That's the red line, right axis, that's here. That's this point here. Down, that's about 30 degrees. 30 degrees of phase margin if you want a peak overshoot under 2.0. And what if you want the damping equivalent of a damping ratio of 0.6? What phase margin would you want? Let's see, damping ratio of 0.6 here. Well, that's about 60. You want about 60 degrees of phase margin. Be the equivalent of a 0.6 damping ratio. One more thing. Note that, remember these omega sub c, the crossover frequency or the cutoff frequency? That's where your gain plot of the forward path transfer function goes through 0 dB. For frequencies much less than that cutoff frequency or crossover frequency, you've got multiple dBs, which means a lot bigger than 1. So your gain is going to be much greater than 1. And to the right of that, because typically they'll go down. To the right of that crossover frequency, it keeps getting smaller in dB, so it's much less than 1. Screwy things can happen. We're going to kind of ignore those. This is a typical loop Bode plot. And I'm not going to go through all this. The bottom line is we'll just approximate bandwidth very simply. It's just twice that crossover. So you can read this graph and find where what that crossover frequency is. And it looks to be about 3, I guess. In this case, a little less than 3. Your bandwidth, we call it about 6, 5 or 6. Very rough, but this is, again, all very approximate stuff. So what can we find out? And some of this goes back to the previous videos. What can we find out from the Bode plot of the forward path transfer function about closed loop system behavior? We find out system type, error constant, and therefore the steady state error, measures of relative stability and absolute stability, primarily using phase margin. I'm kind of not teaching this just because we tend not to use it. But if your course uses gain margin, it's in these charts. I just didn't talk about it. We can talk about peak overshoot. We can find or approximate peak overshoot in the time domain, in the resonant peak, which is the overshoot in the frequency domain, all based on the phase margin. We can find that cutoff or crossover frequency and therefore approximate the closed loop bandwidth. These are all things you're finding out about the closed loop system from the Bode plot of only the forward path transfer function. I'm not going to go through all this because I'm going to go through many examples of all this, Bode plot by Bode plot, and everything you can learn about the closed loop system. I'm going to go through a bunch of examples in subsequent videos. I'll save that for those subsequent videos. Happy New Year.